Hi, I'm Mrs. Hannah Angelin. In this video, we are going to discuss about how deflection and rotation can be determined for beams and frames by unit load method or virtual work method or dummy load method. Virtual work may be defined as work done by the real forces due to virtual displacements or work done by the virtual forces during real displacements. Virtual means imaginary. We shall see the principle of virtual work. It states that if a deformable body in equilibrium under a system of forces is given virtual deformation, the virtual work done by the system of forces is equal to the internal virtual work done by the stresses due to the system of forces. So work done is given as the product of force into displacements. If the displacements are taken to be virtual, then the work done will also be virtual. In this method, to determine the values of displacement, it can be either linear displacement or angular displacements, that is denoted by delta or theta. It will be integral 0 to L, that is the segment length. I write capital M, small m by EI into dx, where capital M denotes the bending moment about a section due to given load system. Small m, it is the bending moment about a section due to a unit load or moment acting at a point where deflection or rotation has to be determined. If deflection has to be determined, unit load has to be given. If rotation has to be determined, unit moment has to be applied. Moment expressions are written. L is the span of the portion considered. E is the Young's modulus or modulus of elasticity, and I is moment of inertia. Let us see some solved examples based upon this virtual work method or unit load method. Let us consider a step beam of span 8 meters. 5 meter is between A and the loaded point C, and 3 meter between C and B. It is given in the problem. The load is acting at the junction, that is at C. Value of E and I is given. Our aim is to find the vertical deflection at C by virtual work method or unit load method. We need to find out what are the reactions at A and B. So for the given load system, it is visualized as a simply supported beam with a load at a distance of 5 meters from end A. With this load, I determine what is the reaction at A and B. So at A I have W B by L. If this is A and this is B, I have 10 into 3 by the length is 8. For reaction at B, I have 10 into 5 by 8, W A by L. The reactions are made a note here. To determine the vertical deflection at the loaded point, that will be a first step. To determine the vertical deflection at point C, a unit load has to be given at point C and all the other loads being removed. So if deflection has to be determined, a unit load has to be given. Our next subdivision is determination of rotation at the junction, that is at point C. If rotation has to be given, all the given loads has to be removed, and at the point where rotation has to be determined, a unit moment has to be applied and moment expressions are written. For this first case, a simply supported beam with this unit load, I have determined what is the reactions at A dash and B dash. Just for variation, I have put dashes. So RA dash, RB dash is determined. Next step, determination of rotation at C. Since rotation has to be determined at C, all the given loads are removed and a unit moment is applied at C. With this moment, reactions are calculated at A double dash and B double dash. We get the equations of RA double dash and RB double dash. With these values of reaction and direction, we are going to draw in the given beam and take sections and write equations to determine delta and theta at C. Here I have marked a beam with a unit load at C alone. Same way, the beam is marked with a unit moment at C. Whatever I am going to write for this beam given loading, that is taken as capital M. For this beam, where I have taken a unit load at C, whatever expressions of M I write for this beam, I take for my calculation of M delta at C, displacement at C. For this beam, where I consider the unit moment at C, I take the moment expressions for calculation of M theta. The reaction directions are drawn. Based upon the reaction and sections considered, I write moment expression about each section considered. So in segment AC, a section is considered from A. At section BC, section is considered from B. Same sections with same origin has to be considered in all these patterns. So I require capital M expression. I require M delta expression with a unit load at the point where deflection has to be determined. I need M theta expressions, that is the moment expressions for this beam about this section when a unit moment is given at the point where rotation has to be determined. Now check this tabulation. I have two segments AC and CB. The length of each segment will be the limits of each 0 to 5 and 0 to 3. So the limits are made note here. Capital M expression, that is due to the given load system. First diagram, I consider RA into X, the moment about the section that causes a moment pushing the beam down or sagging moment. Just to keep your hand and see, it causes a moment which pushes the beam down towards the section. So RA into X is a positive bending moment. Next, towards the other side again, I have RB into X. Again, it causes a moment pushing a beam down when it is taken towards the section. So plus RB into X. That is my capital M expression. There are two segments we have determined. Next, to write M delta expressions. Same sections are considered with same origin. Limits are same. Moment expressions are written with RA dash into X. Even that causes the sagging bending moment pushing the beam down. RB dash into X pushes the beam down. So even that is positive bending moment. Next, I go to the third diagram and write expressions. RA double dash comes down, RB double dash goes up. Since it comes down, when I am going to take a moment about the section, this pushes the beam up. Just keep your hand and see. When it takes towards the section, the beam is pushed up. So this is a hogging bending moment, or it causes a negative bending moment. So I write minus RA double dash into X. Towards the right side, RB double dash into X causes a moment which pushes the beam down. So sagging bending moment. So I put here plus RB double dash into X. And EI variation is shown here because it is a step beam. In unit load method, deflection is written as integral 0 to L mm dx by EI. This m I have differentiated as m delta to determine the value of deflection. Same expression I have given for rotation. To find the value of theta, again integral between the limit 0 to L mm dx by EI. This m is differentiated with theta, telling this moment expressions has to be taken for calculation of theta. Capital M expressions remain the same, that is written due to the given load system. So from this tabulation, capital M expressions and M delta expression for each segment has to be taken, summed up, integrated between the limits, and finally we get the value of deflection. Same way theta rotation is given in terms of radians. Integration has to be done between the limits for each segment, summed up, finally theta c can be obtained. So it is m theta dx by EI. Since EI is twice for the first section, that is AC, I put 2EI. For the next right segment, it is just 1 time EI. So capital M theta by EI into dx integrated between the limits of each section. The values of delta and theta are determined. So here in this problem, we can determine the value of deflection as well as rotation. So this is an advantage of using virtual work method or unit load method. This method is named as unit load method because we are assuming a unit load at the point where deflection or rotation has to be determined. One expression is written with the given load system and the other expression is written with a unit load at the point where deflection has to be determined or rotation has to be determined, and expressions are written integrated to get the final result. Next problem. An overhang beam. The loading is shown in the problem. We need to find delta VC, the vertical deflection at C. With the given loading, we have determined what is the reaction at the supports A and D. To determine the deflection at point C, only a unit load has to be given at point C and all other loads are removed. Check this diagram. All the given loads are removed. Only a unit load at point C because delta VC is asked. Since vertical deflection, I have given a vertical load. Since at point C it is asked, at C we have given a unit load. With this unit load only, we are going to determine what are the reactions. Let us take A dash and D dash for differentiation. We determine the value of RA dash, RD dash. Taking moments about any one support. We have static equilibrium equation, sigma m equal to 0, sigma v equal to 0, sigma h equal to 0. Based upon these three static equilibrium equations, we determine the reactions at the support. Now, we write expressions for integration. Sections are taken based upon the load and the point where deflection has to be determined. AB is taken as one section, BC is taken as second section, from C up to the support D is taken as one section, from D up to the cantilever end it is taken as the other section. The whole of UDL has the same intensity. We take sections and moment expressions are written in each segment. Limits of each section is nothing but the lengths of each section, which you have considered. Moment expressions are given notation capital M for the given loading system. When I am going to take a section in AB, a section at a distance of x from A, you can take from right side or towards the left side. So RA into x causes a moment pushing the beam down. So I have plus RA into x. See in the tabulation below simultaneously when I explain. RA into x, it is positive, sagging bending moment. Next, C for BC. BC is an intermediate section. Whatever is the reaction, even that causes effect when a section is taken in an intermediate segment. So from A, I have RA into the distance from A up to the section is x plus 1. And I have 20 into x. Both causes two types of moment. One causes a sagging moment and the other causes a hogging moment. Sagging means pushing the beam down, hogging pushing the beam up. So values are given in this tabulation. Next, for the same structure where deflection has to be determined and the type of deflection, whether it is horizontal or vertical, based upon it, a unit load is given at the point where deflection has to be determined. Same sections with same origins are taken. Origin is the starting point of x in each segment considered. For capital M and small m, the segments should be same, the origin should be same, limits will be same. So for the same sections, I write A dash and D dash when a unit load is applied at the point where deflection has to be determined. RA dash into x, positive bending moment, pushing the beam down. So plus RA dash into x. RA dash into x plus 1 or 1 plus x. When I go to the segment CD, I have RD dash into x. That causes a sagging bending moment. So plus 2 by 3 of x. And finally at this portion there is no loading. no bending moment, so 0. So I've written expressions for capital M with the given loading system. Wherever I have a sagging bending moment, it is a positive bending moment, I put positive values. Where I have negative bending moment, or if the beam is pushed up due to the load, then I put a negative sign. I write capital M expression. So same beam with same sections, same origin, but devoid of any given loading, but with only a unit load at the point where deflection has to be determined. With that unit load, reactions has to be calculated and moment expressions has to be written at the same sections. Finally, the tabulation is filled. Delta is given as integral 0 to L m dx by EI. So here capital M is the expressions due to the given loading. M delta is the expressions written in the tabulation for a unit load alone acting at the point where deflection has to be determined, and limits are the section lengths. So since there are 4 sections, each is substituted. Finally, the output is obtained. Let us see the third problem. Vertical deflection and horizontal deflection has to be determined for this cantilever frame at point C. When I write bending moment expressions for the given load system, I take the notation as capital M. When I write bending moment expressions with a unit load in the vertical direction at C, I take that for my vertical deflection calculation. I write the notation M delta V. When I give a horizontal unit load, write bending moment expressions, I take the expressions as M delta H. So there are 2 types of deflection that has to be determined at C. One in the vertical direction. So I am going to give a unit vertical load at the point required. Next is horizontal deflection at C. So at C, I am going to give a unit horizontal load, then analyze to find the values of deflections. A unit vertical load acting at point C to find the vertical deflection, and the other due to unit horizontal load at C to determine the horizontal deflection. So each free body diagram is drawn here. I'll explain one by one. From C, when I proceed towards E, there is no loading. At E, I have a load of 15 kilonewton. So opposite to this is marked here, equal and opposite to the load. At joint B, to be in equilibrium, it should have equal and opposite internal reaction. For the column to be in equilibrium, this 15 has to be opposed by another 15 here, equal and opposite, equal in magnitude and opposite in direction. This 15 kilonewton is acting at 1.5 meter from point B. So there will be a moment caused due to 15 kilonewton in the clockwise direction. The value is 15 into 1.5. So here at B, it should have a resisting moment 22.5 acting in the anti-clockwise direction to that of the clockwise moment caused due to 15 kilonewton. At joint B, to be in equilibrium, equal and opposite transfer to the other end, equal and opposite. The reaction due to the loads and moments are transferred at joint B to the column. So now taking these reactive forces and proceeding towards the other end to write my moments and internal reactions. So when I start from B and proceed towards A, I have a load 10 kilonewton. It is at a distance of 2 meter from A. This 10 kilonewton will be having a horizontal reaction in the opposite direction, equal in magnitude, opposite in direction. 20 kilonewton meter will be the moment caused by this 10 kilonewton acting in the clockwise direction. So resistance will be in the anti-clockwise direction, 20. If you need to find what is the reaction from this free body diagram, the algebraic summation of all the moments at A will be support moment at A, horizontal reaction at A, and vertical reaction at A. This diagram has to be considered for writing my capital M expression. Next, let us draw free body diagram for writing small mv expression, that is to find the vertical deflection at point C. We have given a unit load. For that, we need to draw the free body diagram. So this load is opposed internally. You have internal reactions here shown in green color. So this load is acting at a distance of 3 meter from B, 3 kilonewton meter acting in the clockwise direction. So resistance at the other end will be in the anti-clockwise direction. For equilibrium, equal and opposite at the same joint, and again for equilibrium, equal and opposite in the column. So starting from C and proceeding towards A, I have no other loading. So this free body diagram has to be considered for writing my MV expressions. Next, my MH expression. Here I have given a unit horizontal load at C to determine my horizontal deflection. With this unit load, internal reactions are marked equal and opposite starting from C and proceeding towards A. This is acting axially till B. So at B, check the direction of 1 kilonewton. It is acting axial. From this point B up till A, the distance is 4 meter. The moment caused due to the unit internal reaction will be 1 into 4 acting in the clockwise direction. Resistance will be in the anti-clockwise direction. So this diagram has to be taken for writing my MH expressions. Or pushing the column inside and beam inside is taken as positive bending moment. So depending on that, the moment expressions are written in all the 3 diagrams where we have drawn the free body diagram. Let me explain for one. Let us check the first diagram. So here starting from C up till E, there is no loading. My capital M expression turns out to be 0. Then in the next segment from E up to B, there is a load here, so it is divided into 2 segments. From E up to B, there is a load 15 kilonewton. Distance up to this section is X. That pushes the column up when it is moving towards a section. So minus 15 into X will be the moment about the section here in BE. The moment is a negative bending moment. So we write here as minus 15 into X. Next, when I go to the column BA, again there is a loading dividing the column into 2 segments. In segment BD, starting from B till D, we need to find if there is any sagging or hogging bending moment taking place. This 15 is acting axial. That doesn't cause any bending moment. This 22.5 kilonewton meter, previously we have determined the values. That causes a moment towards a section such that the column is pushed out. It is taken as a negative bending moment. So 22.5 is written with a negative sign. Minus 22.5 in dB. Next, proceeding to the last segment dA. Whatever is the reaction that from B has to be taken. If any load, even that effect has to be taken. 15 is axial, no moment. 22.5 pushes the column out, so minus 22.5. 10 into X again pushes the column out if it is taken towards a section, so minus 10X. Okay. So in the same way you can verify for M, H, MV expressions. It is filled up here based upon the direction of moment caused. Finally, integration is carried out between capital M and MV for delta VC and capital M and MH for delta HC. Since we had 4 segments, for each segment we have the expressions in the tabulation. You can substitute to get the values for delta VC. Same way delta HC. Let us see another frame. A simply supported frame. A is hinged, D is roller. It carries loading as shown in the figure. We need to find the horizontal displacement at the roller end and rotation at the roller end. By now you should know in unit load method or virtual work method, if horizontal or vertical deflection is asked, we need to give a unit load in the direction in the point desired. And if rotation is asked, we need to apply or provide a unit moment at the point rotation has to be determined. So now delta HD has to be determined. So at D, we need to provide a unit horizontal load. It can be along positive X or negative X direction. Next, to find theta D, a unit moment has to be applied at D. It can be in clockwise or anti-clockwise direction. To begin with, let us assume a horizontal load at D in the positive x direction and a moment in the clockwise direction. So capital M expressions are written for the given loading. MH expressions are written to find delta H. So this is written with only, note the word, only a unit load at D and divide of all the loads in the given frame. Next, to find theta D, we provide a unit moment only at D and divide of all the given loads given in the problem. We are going to find the reactions. We are going to find the free body diagrams for each loading patterns. Same sections in all the three frames. Origin will be the same. Limits will be the same. Delta HD can be calculated by integrating the expressions between capital M and MH. And theta D can be determined by integrating the expressions between M and M theta. Let us see how this is possible. We make use of these static equilibrium equations to determine the reactions at the support. So with the given loading, we have taken moment about A, we have applied sigma V equal to 0 and then determined what is the value of reactions at both the support. Here we have removed all the given loading, applied only a unit load at D because deflection has to be determined at D in the horizontal direction. Due to this, the reaction is determined. So HA is possible, equal and opposite. Sigma H is equal to 0 is the equilibrium equation used. Since the horizontal load is at the support, there will not be any reaction, vertical reaction at the support. Check the third diagram. A unit moment is applied at D. Due to this, what is the direction of reactions and magnitude of reactions are dealt here. So for these three frames, for three loading patterns, the reactions are separately determined. Next, we shall draw free body diagram for each frame. Let me show you for the given loading pattern. All the loads are shown. Let me start from the left end. RD we have determined as 19. So starting from D, proceeding towards the other end. This is the free body diagram for the given loading pattern. So RD is acting in this direction. It will have an equal and opposite force at all the joints, bends or the supports. RD is acting in the upward direction. For the members to be in equilibrium, each end of the member will oppose this 19 kilonewton. It will have an opposite direction force but equal in magnitude. At joint to be in equilibrium, again it will have an equal and opposite force. This 19 kilonewton till C, it will be an axial force. Since it has a distance from D to A, RD causes a moment at joint B because it is separated by a distance of 5 meters. Here it doesn't have any moment because it is an axial force. Here it doesn't have moment because these two are the same point. A joint B will have the resisting moment for this RD. Check the direction. It goes in the anti-clockwise direction. So resistance will be in the clockwise direction, 19 into the distance 5. You can see here, 19 into 5, 95 kilonewton meter. Check the direction, opposite in nature, equal in magnitude, and other end, since it is spin, it will release the moment. This we have drawn. You have a 5 kilonewton load, equal and opposite. Check the colors. I have differentiated. 5 kilonewton, equal and opposite at each joint and at the end of each members. This 5 kilonewton causes a moment of 5 into 2.5 acting in the clockwise direction when moment is taken about C. So at C, it will have a resisting moment opposite in nature and opposite in nature at each joint. Here it is spin, so no moment. Next, after this, we proceed to the beam. At joint C, it is the starting of UDL. So here we don't have any reaction or moment. So starting from here, proceeding towards the other end, you have the effect of the total load of UDL, that is 25, acting in the downward direction. So here at the joint B, it should have a resisting force of 5 into 525. That is the total load. Total load has to be resisted at joint B. So equal and opposite, equal and opposite. This UDL will cause a moment about B. Resisting moment will be 5 into half the distance. So the UDL will cause a clockwise moment. Resistance will be in the anti-clockwise moment. And then that is transferred. With these expressions, at sections considered, we are going to write moment expressions. If it is a sagging bending moment, that is, if the moment pushes the column or beam inside the frame, it is taken as a sagging bending moment or positive bending moment. Here let us consider, for an example, 5 into x, a moment caused by phi about the section. When it causes a moment towards a section, that will push the column outward. So it is minus 5x because it is a hogging moment. Let us consider this portion. Let us consider for BE, we have taken a section. So at B, we have two loads acting axial. We have 5 kilonewton acting perpendicular to BE. There are set of moments. 5 kilonewton has a perpendicular distance, but check, it is acting towards the section, pushing the column inward. So it is a positive bending moment. So 5 into x will be a positive bending moment. Check 95, again it pushes the column inward when it goes towards section. 95 is a positive bending moment. Check 12.5 and 62.5, both pushes the column out. So these two are negative bending moment. This is followed in writing the tabulation. Let us see the free body diagram for the next loading pattern. That is with the unit load at D alone. At each joint it is resisted and it is transferred to the other end. This 1 kilonewton is 5 meter from C, causes a moment in the anti-clockwise direction. So internal resistance at C will be in the opposite direction. And that moment is transferred. At A it is spin, so moment is released. Next, m theta. So giving a unit moment at D alone and devoid of all other loadings in the given problem. So here, starting from D, we didn't have any reactions here in the vertical direction, so we didn't mark any reactions in the previous case. So here we have reactions due to the moment we have determined in the first step. So for this reaction, we have drawn all the axial forces opposing each. Next, this reaction will cause a resisting moment at joint B since it has some distance. So 1 by 5 into 5 will be the moment caused at B. So that is shown in blue color, equal and opposite. This 1 kilonewton which you applied will have a resisting moment at the other end and it follows a particular sign. With these moment values, expressions are written about the same sections considered and that is shown in the tabulation. This frame is divided into 5 sections based upon the loading. Origin is the starting point of the section considered. It should be same for capital M, M theta and MH. Limits, only then it will be same if the sections considered are same. EI, since it is constant, EI is written as it is. Capital M expressions are taken from the first free body diagram with the given loading pattern, whether it is a sagging bending moment or hogging bending moment. Same way MH is written from the diagram where we have given a unit load at D. M theta is the expressions written for diagram where we have given a unit moment at D. Integrating between capital M expressions and MH expressions between the limits shown here for each segment and summed up will give the values of delta H, and integrating between capital M and M theta expressions between the limits given will give the value of theta D. That is shown here. So these are the values obtained as a result of integration. So in this video, we have discussed how unit load method or virtual work method is applied for simple determinate beams and frames. Here in this method, we have calculated deflection and rotation not only at the loaded point but also away from the loaded point. That is an advantage of using this method.